Okay, so here we're supposed to find the area of each circle. So let's take a look. So I'm noticing that we have segment AT, which is a tangent, and I know that because it's marked that way. You can see the 90 degrees, and it's intersecting the circle at one point. So because I have the 90 degrees, I see a right triangle. So I can use the Pythagorean theorem to get that missing side. And the reason I want to get that missing side length, AC, is because I'm noticing that AC is a radius of the circle. And I know to find the area that I'm going to need to know the radius, because area is, we know, pi r squared. So let's use the Pythagorean theorem to get the length of AC, and then we'll know the radius. And then once we know the radius, we can find the area of the circle. So we have short leg squared, a squared, plus 4 squared equals 5 squared. So we can use the Pythagorean theorem to solve this. Or some of you may know the Pythagorean triples, and you may already know what a is just by looking. But let's go ahead and use the Pythagorean theorem. So a squared plus 4 squared is 16, 5 squared is 25. Subtracting 16 from each side gives us a squared equals 9. And taking the square root of each side, we're getting, remember, we care about the positive number here only, so a is equal to 3. Okay, and Pythagorean triple, if you knew that, a common right triangle has lengths 3, 4, and 5. That's called a Pythagorean triple. So some of you may have known that AC was 3 even before we used the Pythagorean theorem. So we know that, so now we can use area equals pi times the radius squared. We'll substitute 3 in for the radius. 3 squared is 9, so 9 pi is the area of this circle. And of course, these are square units. Looking at the next one. So I see a 3 for the long leg, and I see 2 root 3 for the hypotenuse. It's looking like perhaps this could be a 30, 60, 90. And the reason I say that is I'm recognizing the square root of 3, and I know that x root 3 and 2x is the ratio for 30, 60, 90. However, even though I'm suspecting that it's a 30, 60, 90, I can't assume that because the only angle marked is the 90 degrees. So I am going to go ahead and use the Pythagorean theorem to see what the short leg is equal to, and that also, once again, is the radius of the circle. So I have 3 squared plus a squared or b squared, doesn't matter, is equal to 2 root 3 squared. So 3 squared is 9. Just separate these problems a little bit. Plus a squared is equal to, and now what we're doing here, remember when we're squaring 2 root 3, we're doing, give myself a little space here. We're doing 2, I don't know why that happened. We're doing 2 root 3 times 2 root 3. So I have 9 plus a squared is equal to 2 times 2 is 4, and root 3 times root 3 is 3. So I have 4 times 3. So 12 is equal to 9 plus a squared. Subtracting 9 from each side gives me a squared is equal to 3. And taking the square root of each side, a is equal to the square root of 3. So we are getting the square root of 3. So now that I see the hypotenuse is 2 times that, I have just confirmed that this is a 30, 60, 90 triangle. But anyway, we know the radius. That's all we really care about. And let's use it to get the area. So the area is equal to pi times the radius, which is the square root of 3 squared. So square root of 3 squared, that's root 3 times root 3, which is just 3. So the area is 3 pi units squared. Okay, next. A segment of a circle. So we know what a line segment is, but this is different. This is a segment of a circle. So this part here that is highlighted or shaded in blue, that's the segment of the circle. Okay. Now, with a segment, what we generally want to do is find the area of that segment. So the way that we do that is I'm first going to find the area of this whole sector. Now you should be familiar with sector. We already talked about that. So this whole section right here, if I shade that in purple, that whole sector is, we can find the area for. Now if I take the area for that sector and I subtract the triangle area, if I can make that a different color, so we can see the area of the triangle. Okay, so if I subtract the whole sector area, which was the purple, and I subtract the red, that will give me what's left, which is the blue. So let's go about finding that. So let's first get the area of the sector. Okay, so we know to take pi times the radius, which is 3 squared, and we're going to multiply that by, this is a 90-degree angle, so 90 over 360, and that'll give us the fraction of the circle that the sector is contained in. So we're getting pi times 9, and 90 divided by 360 is 1/4. So I'm multiplying 9 pi times 1/4 and getting 9 pi over 4. And that is in square inches. So that's the area of the sector. Now let's get the area of the triangle. So the area of the triangle I know is base times height. Well, I have the height filled in already, but I need to figure out what the base is. Well, you should be noticing that this is a circle R, which means that R is the center, which means the side that's marked 3 inches of the triangle is the radius of the circle. Well, so is this side the radius, so that means that's also 3 inches. So now I have the base and the height. So 3 times 3, base times height, divided by 2, or times 1/2, is the formula for the area of a triangle. So that gives me 9/2 inches squared. So if I want the area of the segment, I'm going to take 9 pi over 4, and I'm going to subtract 9/2. And when I do that, that's my exact answer, first of all, that inches squared. That would be my exact answer, but I can certainly get a decimal approximation by typing that into the calculator. Okay, so I entered 9 pi divided by 4 in my calculator and got approximately 7.07. 9/2 is 4.5. And when I subtract 4.5 from 7.07, I get that the area of the segment is approximately 2.57 inches squared. And that's how you find the area of a segment. I'd like you to try problem numbers 5 and 6A and B on page 34 to get practice on some similar problems.